Okay, thanks for the feedback.
Is anyone here willing to take notes for us? It's a very simple job.
Okay, we have Chris off. Thank you.
Can you repeat that, Sarah? Sorry.
So Christopher Patton has offered in the chat to take notes. Thank you,
Excellent.
Christopher.
Thanks, Chris. Should we get started? Yeah, let's get started. Do you want to kick it off?
Hey all, welcome to the PEARG session. We are your chairs. I'm Shivan, we have Chris and Sarah joining remotely. I guess Sarah, you're sharing the slides anyway. Do you want to go to the next one?
Sure.
Yeah, thanks. This is the note bell. Please note it well. Also, please note that according to IETF policy, we do have to wear masks inside all meeting rooms. So just be aware of that. And let's move on to the next slide. Yeah, so this is the agenda. We have 3 presentations and a quick update on draft safe measurement, I believe, that Mallory will be giving. So we have, I guess the chairs can do Jabber's, keeping an eye on Jabber, and we have a minute taker. Thank you, Chris Patton. And I think we can start. So if Sophia is online.
Yes, I am here.
Do you want to present your slides?
Yeah. Do I have to share them or do you share them? Oh, there you go. Okay, it's been shared. I'll wait. Okay, I see the slides now and I see on the screen also that they are shown on person. Okay, great. Let me start my video. Okay. Should I just go ahead, Shivan?
Sorry. Oh, sorry, what was the question, Sophia?
Should I just go ahead with the presentation?
Yes, please. Thank you.
Okay, thank you. Hi, everyone. Thank you so much for having me here. My name is Sofia Celia, and I work at Brave Software. And today I was just going to present a very informal note or an informal presentation on privacy-preserving measurement techniques. And as I said, this is just an informal comparison. Next slide, please.
Okay. Sophia, do you see a slide selection at the bottom of your screen that you can drive?
No.
Okay, that's no problem. We'll move the slides along.
Okay, thank you. Sorry for that. Thank you very much, sir. Okay, as a preface, as a little bit of a disclosure, again, this is not a complete overview, but rather an initial note around the different techniques that one can use for indeed trying to attain privacy-preserving measurement techniques. And what it really wants to aim is to answer the question, if I want to execute measurements with privacy, which scheme should I use? And while in general, this likely seems like a simple answer, in reality it's a very complex one, because there's a big array of different techniques that one can use and different schemes. So it's difficult as a user or the system administrator, or just a user who is a system administrator, to actually choose the correct scheme or the scheme that best suits your need. The other problem is also that, as we'll see, we have different techniques and different schemes, and the majority of them really attain a level of privacy and security, but it's difficult to correctly pinpoint and attest which specific level of privacy or security they are providing. There's also unclear expectations of the efficiency of monetary costs that indeed these schemes provide. And if you are interested for some further notes, I have put online this very informal PDF that is going to be developed into something more formal eventually through the months. Next slide, please. Okay, so let's just start from the beginning. Which one is the main notion? The main notion is, of course, that you as a provider of whatever system or whatever application, you want to indeed know something about your users. And the reason why you want to know something about the users is mainly because you want to improve the usability of the system by understanding how indeed users use that system. And while this seems great in practice, at the downside, it has a big bad consequence, which means that we are learning certain private things from users that we are not supposed to learn. And in the light of this, the idea was to actually provide a private and secure way to actually be able to collect these aggregate measurements. Because, of course, as I said, these aggregate measurements correspond to a centralized leakage of private user data. Currently, the IETF actually has a working group devoted to this that is called PPM, that precisely has been trying to standardize certain of the techniques that I'm going to talk about to provide privacy and security for aggregate measurements. Oh, I think I now can do that.
Yeah, you should have control of the slides yourself now.
Perfect, thank you. So a little bit of a wishful thinking. So the first also question that one must pose themselves when actually thinking about it is what level of security and privacy one want to attain. And the first main definition that one might find is this one by Dallenius, which is not specific to taking aggregate measurements on the digital world, but rather in general for a statistical disclosure control. Mainly the privacy and security that it aims to provide is something similar to semantic security, meaning that access to a statistical database should not enable anyone to learn anything about a user that could not be learned without access. And this is a very strong privacy notion that we will see that is achieved to a degree by the different techniques that this survey covers. So let's start with the actual techniques and scheme. And as I said, there's many, so I've tried to categorize in general by the specific technique that they use. The first one is the techniques of differential privacy. And the reason why I'm talking about this in the first place is because it's one of the oldest schemes there are out there to actually preserve privacy for aggregate measurements. And the idea in the differential privacy techniques is that some local randomness, some kind of noise, is added at some points when you're actually performing the aggregate functionality. It could be to the data collector, it could be to the output of the statistical function, or it could be to the mechanism itself. And what in general differential privacy wants to attain is a notion that is called epsilon differential privacy. You will see here a mathematical notation, just don't worry about it, this is just for reference. But mainly if you ever read the papers of differential privacy, this is the notion that they want to attest. And without any mathematics, the meaning is that the output of the function, of the statistical function, is similar on both data sets if you change or remove the one element. So any kind of operation that you take in different data sets, someone looking from the outside cannot differentiate. There's two basic schemes that support differential privacy that here have been actually deployed in the real world. The first one is Rapport from 2014 until 2019. It was kind of supported. And basically what it does is it uses the same idea of adding local random noise into the statistics that is taken from users, and also using memoization. The problem with this scheme is that it is very costly because locally you have to add all of this randomness, and therefore it is very costly. In the light of this being very costly, another system was developed, which is called PEARG. And it's much more efficient and also uses a different architecture. The architecture that it uses is called encode, shuffle, and analyze. It is an ESA architecture. And mainly the idea is that you also add this local randomness, but this one in turn is augmented by a private channel that randomly permutes a set of user supply data. So you have the local one that you add, and in the encoding section, then you have a shuffle part that permutes the different user data, and then you have the analyze one that it just performs the statistical function that you need to perform. What is the problem with this one is that it's more efficient in a way, but it also requires trusted architecture because you indeed have to trust the shuffler in order to be secure, to be assured that indeed the mechanism is working. So there you have a little bit of a downside of PEARG. In the light of these, all of these schemes of differential privacy, I just touched two very lightly, but there are many, many more. As you see, all of them could have a lot of drawbacks. And in face of this, another system was developed that was called PRIO. And nowadays, the PPM working group on the IETF is also trying to standardize some PRIO-based like schemes, not specifically the original PRIO as it was first written in the original paper, but kind of similar schemes. What does basically PRIO want to attain? Basically what we started on the first slide, private aggregation, and also they specifically specified three properties that they wanted to have. Privacy, of course, robustness, and scalability. So this scheme indeed tries to be a little bit more efficient. And the way it works is that it works with a small number of servers and a large amount of clients. And as long as one of the servers is honest, the system leaks nearly nothing about the user's data, except for what the aggregate statistic itself reveals. So as you see here, we have already a little bit of a leakage of the privacy that the system provides, because it's not completely private as the first slide that I showed you wanted, but rather that there is a specific amount of leakage. So for example, let's say that you are using a mean function, you are trying to compute a mean functionality. Therefore, something is leaked, meaning the number of users that have submitted some user data, because you divide by the number of users. So that is leaked by the aggregate function. There's other variations of these schemes that, as I said, has been proposed to be standardized by IETF. You have PRIO Plus, that is a little bit more efficient because it uses Boolean circuits instead of arithmetic circuits. There's PRIO 2, which is not going to be standardized as far as I know, and PRIO 3, which is the one that is going to be standardized as far as I understand. And that one is more efficient into the client-to-server communication. To give you a little bit of a specific pinpoint of the specific privacy that PRIO provides, it uses a specific privacy that's called F-privacy, in which an adversary who controls any number of clients and all but one server learns nothing about the honest client's values except what they can learn from the aggregation function itself. And this is just repeated what I already showed you in the previous slide of what kind of privacy it provides. It's kind of a bounded privacy in the sense that there's some amount of leakage. Yes. I'll take the questions at the end. I see that there's some in the Zulip, but I will take them at the end. Okay, so a little bit of a diagram for whomever doesn't know exactly how PRIO works. This is just a really high-level explanation of how PRIO works. But in general, let's say, for example, that you are a user who is going to a park and indeed is in the park. And then the system actually wants to know if you are in the park, because the mobile clients, for some reason, want to know that what amount of users are actually going to this park. And if you are in the park, then the mobile phone says 1. And if you're not in the park, the mobile phone says 0. And sends this data to a collection of an amount of servers. So instead of sending the 1, meaning the yes, I am in the park, what it does is that it splits this 1 into shares. In the shares, for example, of 15 plus minus 12, plus minus 2, which also map to 1, and sends the individual value to each server that belongs to this system. And as you see here, each individual server will not be able to pinpoint which is the private value that the user is submitting, because it's just a secret share that the user has been submitting to the server. Now, it's important here, of course, that the user is honest in that the range value that they are sending should correspond indeed to that range, meaning that they send either a 0 or a 1, meaning a yes or a no. Sorry, a no and a yes. But for example, let's say that a client sends a 2. In this case, in general, if you're only using secret shares, then that's indeed possible that the user could be sending a 2. So what you indeed also add in the PRIO system is that you add a zero-knowledge proof that is specifically called a secret share non-interactive proof in the PRIO language. And basically, this is a proof attesting that indeed the user is sending the correct value in whatever range. So in an example, is the correct value is either a 0 or a 1, and that is sent. And once that is sent to the different servers, they each gossip between each other and attest to the validity or not. And if indeed it is valid, they indeed aggregate whatever shares were shared with the servers, and eventually they will be able to compute whatever aggregate function they were trying to do. And as you see, this is preserved in the face of a malicious client. But then there's some efficiency drawbacks here, mainly server-to-server communication is efficient, but server-to-client communication is inefficient because computing sometimes these zero-knowledge proofs, while efficient than the previous zero-knowledge proofs, is still much more costly. Okay. And also a thing to note is that PRIO-based systems only work on numeric values, meaning that you can only send numeric values. But if you want to send something like strings, then the system does not completely cover that. In the face of this, there's another kind of problem that one can solve indeed when someone is trying to have all types of data to be part of an aggregate function. And in this case, we call it the heavy hitters problem. One of the schemes on this is the scheme of the star that has been recently been announced in a paper and also proposed to the IETF. Not so recently, I think a year ago. It doesn't, again, focus on the specific privacy problem that belongs to the PRIO system, but rather in another privacy concept, which is called the threshold K anonymity. And basically, the idea is that the server only learns any data from a client, any private values from user, if there's at least K-1 other clients that are submitting this data. And what it prevents is it prevents the data collector from specifically learning uniquely identifying information or uniquely co-occurring patterns of data from a unique client. How does it work? Mainly what it happens is that a client constructs a ciphertext of their data using an encryption key derived from some randomness. This randomness is usually taken from a randomness server that uses an OPRF functionality to actually have this data. Then the client, once it has the ciphertext, sends the ciphertext to the servers, and also a K out of N secret share of randomness, and tags these shares with a specific tags, so the server will know which one to combine. And at the end, the aggregation server organizes the shares into subsets depending on the tags that was just submitted by the client, and recovers the encryption keys from those subsets of size bigger or equal to K. And if you want a little bit more of a beautiful diagram, it is here. As you see here, you have 3 entities. The first one is only to actually gather the randomness in order to be able to derive the key that is going to be used to encrypt the ciphertext. And then the other one is actually the client sending the ciphertext to the aggregation server, who will take the auxiliary tags that the client actually defined, will be able to reconstruct the specific key for that ciphertext, and will be able also to decrypt it. One of the things that is important to note here in specifically of the system is that it's the first system that takes into account not only about efficiency, but also the monetary costs that are associated with running all of these kind of PPN techniques. Mainly the system, for example, one of the aims was actually to have low monetary costs. Another system that is very similar to PRIO is the Poplar system, which also allows for finding the most popular string among a collection of clients, as well as counting the number of clients that hold a given string. The only difference with PRIO is that in PRIO you would require only one on a server. In this case, you have to have two non-colluding data collection servers, and it indeed also preserves the same amount of privacy as PRIO. Okay, so that's a little bit of a really brief overview of the different schemes. But if you are a little bit more interested in how actually you compare to each other, which was the core of the question when actually having this note, I kind of created 2 tables for this. On the first time, for example, it's good to consider the type of data that you indeed want to use when you're actually thinking about choosing some schemes. So as I already said, the PRIO-based functionality somehow some numeric, and then the StarWorld has some string, other kinds of types of data that it can indeed be accepting. There's also some types of robustness notion, for example, where I say that in some systems, for example, the trust assumptions are different in the sense that at least one server has to be trusted, and on others, they don't actually require any kind of trusting entity. Also, as I said, while all of them provide certain kind of privacy notion. None of them actually attain the original privacy notion that I just put you in the second slide, but rather all of them have some kind of leakage. In the case of pre-assistance, for example, I already mentioned that the leakage that they have is whatever that the aggregate function leaks itself, that's leaked. In the case of a star, for example, the server learns which clients share the same measurements. In the same of Poplar, there's a leakage of all heavy hitting prefix. All of them also have different efficiencies. So we already saw that in the previous PRIO-based systems, you have an inefficient client-to-server communication that is improved in the iterations of the original PRIO paper. So you have a better efficiency in PRIO 3. And I only added the monetary cost of the two last schemes of Star and Poplar because those are the only ones that I have seen analyzed for the monetary cost. Perhaps what is missing in this table is properly inputting for the other schemes, but I didn't have a lot of time to actually analyzing them from the monetary cost. Okay, so that's a little bit of comparison. And if a user wants to at least choose between all of these different schemes, you see there's a lot of values to actually compare and attest if indeed it works for your system or not. Something that is also interesting to note is that the user needs are most of the times absent from any of these kind of studies or even in the original designs, in the sense that the voice of the user is notably absent. And while it's great that these kind of schemes are advancing the privacy of the user, at the same time, sometimes users will not be wanting to participate in different aggregate functions service or in different kind of service in general. And the reason why they will not be wanting to actually be part of the systems is because while maybe the system, if they provide some privacy and not going against individual privacy, they might go against the whole group privacy. For example, let's say that you have a survey about women and about the number of abortions that women have. I would like to participate in that kind of functionality, even if the system says to me that it's private, because the output of that functionality of that function might be used to harm me as a woman that belongs to the woman group or as an individual that belongs to the woman group. So the point here is that while it's important to provide privacy, it is not enough. It also has to take into account user consent, and also, yes, it also has to take into account user consent, which should be really noted and really important into the different design systems. And with that, thank you very much. Sorry, I'm running out of time. So yes, sorry, thank you very much.
All right, thank you, Sophia. Unfortunately, we don't have time for questions, so we'll have to move on to the next presentation. Sophie, there's a number of questions for you in chat. I'm sure you could engage with those folks further there.
Yes, thank you.
All right. So next up we have Bharath. Can you request to share the slides?
Okay, can you hear me?
Yes, we can hear you.
Okay.
Hold on. One more time.
Okay.
Okay, take it away.
Okay. Thanks for having me. So I'm Bharath Raghavan, faculty at USC and co-founder in Visiv with Paul Schmidt, one of my colleagues. And thanks in this to Jana and Chris and Tommy for a lot of the discussions that went into this. So I'm going to give a very high level talk, very different type of talk, really trying to step back about this question that some of us have been noodling over for a while, which is there are all these interesting privacy preservation network protocols, systems, architectures that have been come up with by a lot of you in this group and folks in the IETF community, in the network systems and privacy community for years, decades, really. And we were trying to figure out what is in common among all of these, the ones that we think actually achieve some sort of meaningful and practical privacy preservation. And it seemed like there may be a sort of a common principle that doesn't sort of address all of the questions that we care about, but one of the core sort of design principles that may be underlying them. And so that's what this talk is about, what we're calling the decoupling principle. So at a high level, basically the decoupling principle is for internet privacy, you want to decouple who you are from what you do. That's the nutshell of this talk. is an old idea, is nothing new that we've come up with here. Chom introduced this in 10 different ways in a classic series of papers back in the 80s and then in the 90s. But it's been inconsistently applied over the decades. For some reason, this principle sort of gets rediscovered over and over again, and then it gets forgotten, and then it gets rediscovered. It seems like right now we're in a phase and an era over the last several years where people have rediscovered this principle and are using it to good effect. And a lot of the proposals that have come out from many of you, again, have used this principle. And so what we thought we would do is just step back for a second and think about what's going on in a lot of these systems that enables internet privacy by decoupling who you are from what you do. And it seems like decoupling is easiest when we split by entity, so meaning who are the different parties in the network that are participating to achieve some internet service, and the mechanism that's being used. So the mechanism might be a mechanism for authentication or mechanism for connectivity or for whatever else that you're trying to achieve. The decoupling is always going to be protocol and context specific. So you have to look at the specific service that you're trying to provide, of course. So we can go through that for a few examples and very sort of at a high level trying to understand what kind of decoupling is being achieved. So the context here, before we go into that, is ordinary data confidentiality is nearly solved. This is sort of a broad statement I'm making here, but we're at a point where TLS is everywhere, data is encrypted at rest, and if it's not, we know that we need to do those things. There are some hurdles in some contexts where you can't use TLS, or you can't encrypt data at rest, or you can't do some of the very well-known steps for data confidentiality, but we know we need to do those things. So the solution is there, it's about implementation. But what remains is this a little bit more complex layered metadata privacy problem. And this is in many different contexts at different layers of the network stack, everything from the mobile layer to various types of internet protocols to applications. And so you need many different overlapping solutions. And so it's not that you would apply the decoupling principle for a single user in a single context in a single protocol and then be done, but rather that you want to decouple all the things effectively. And really the privacy challenges that we're dealing with here are fundamental to the internet, maybe in a unique way versus all other sort of computing contexts, because we rely upon others to carry our traffic and process our requests. This is sort of a fundamental thing with networking that's not true in other domains. And so, you know, a lot of computer science now is focusing on privacy and security, but they don't have the same degree of challenge for privacy as I think we do. So a little bit of terminology, trying not to make it super terminological, but, you know, just to be a little bit more clear about what we're talking about. So we're going to have a very crude binary distinction between sensitive and non-sensitive information. And that's the level we're going to stay at. It's a very high level. This filled triangle is going to be sensitive user identity. So this is, you know, my name, or maybe in some contexts, my home router IP address. And the hollow triangle is a non-sensitive user identity, some sort of temporary identifier or random identifier. And then sensitive user data, again, is going to be context specific, but it could be everything from the actual contents of a request that I make to some service, or the response that comes back. And non-sensitive user data would be, for example, the fact that I did make a request, but no content of that request. So then we can describe using, we just have sort of a tuple, which will say, there is some party in some context that has some knowledge about the user. And we're going to talk from a single user standpoint for the moment. So if I write it like this, sort of a filled triangle and a hollow circle, then we're talking about somebody knows sensitive user identity and non-sensitive user data. So how do we apply this? So we'll go through a couple of examples using just existing systems and think about what the decoupling going on is. But first, there are some caveats, obviously. Identity and data are always shades of gray. The idea that we can say this is sensitive user identity and this is not, it's really difficult to cleanly categorize that. But you know, that's we're going to sort of use these generally understood categories for the analysis, and then we can complicate it through thinking about side channels and all the shades of gray that also come about for a user identity. The same thing, of course, is true with data. The data itself, there's shades of gray of what counts as sensitive and non-sensitive, and maybe even contextual. Some data might be sensitive in one context and not sensitive in another. The user is ultimately going to be the judge of that. And then, of course, further still, identity and data are sometimes mixed and conflated. And so there too, this is going to be complicated. So I'm going to just sort of put those caveats out there, but also we're going to ignore them for the moment and think about the simple case first. So let's just look at something we all know, something like mixnets or Tor. And in this context, we have some sender trying to send a message, some request or data to some receiver over this network. And they're trying to achieve some data or metadata privacy for their identifier, their personal identifier, and the message that they're sending. The mixes are some third parties that are relaying the data. And then the receiver is a partially trusted party who will receive and respond to the message. So that's the setting that we have. We don't have to go into the specifics of a specific design for this analysis. So in this context, the sender, of course, has all the sensitive information. I'm the sender, I'm the user, and I know, of course, my identity, so the triangle, and the data that I'm requesting. So that's the filled circle. Now, the first mix here knows my identity in some form, in the sense that I have to talk to them. So they know my IP address, or they know some sort of network identity of me, for me. And then the subsequent hops know less and less. So they don't even know who I am. They just know that they got a message from somebody. And there's the request itself, which they don't know. Now, there's also the context in which I could pretend to be mix number one. So mix number one actually thinks that I'm sending on somebody else's request, right? There's that design in some systems. So mix one may not know even my identity. So let's leave that out for a second. And then finally, the receiver is going to get a message from somebody. They don't know who, unless I specifically conveyed it to them. And that's going to be non-sensitive user identity and sensitive user data potentially, because I am sending a specific request which they are capable of decrypting, so that they can then give me a response, or maybe I'm just sending them data for their sake. So if you look through this, you see that only the sender knew both sensitive identity and sensitive data. And so the basic idea, the decoupling principle, is really simple. Third parties should know at most one of sensitive user identity and sensitive user data. And so some of them might know the identity piece, but not the data piece. Some of them might know the data piece, but not the identity piece. And it's not always simply there's one type of identity and one type of data. In some systems, there are multiple types of identity. One of the systems I'll briefly mention is it has a mobile identity piece and a non-mobile identity piece. There's lots of other similar kinds of systems. So this has been used all over the place. There's all of the classic designs from CHOM and all the systems that have built upon CHOM's designs. They all exhibit the decoupling principle. Privacy pass and private access tokens exhibit the decoupling principle. In that context, you have a client, an issuer, and an origin. The issuer and origin, neither of them know both the identity and the data. In the context of oblivious DNS and ODO, the resolver and the oblivious resolver, also, they know either the identity or the data, but not both. Same with the origin. In the context of pretty good phone privacy, which is one of our systems, this is one where we have a mobile identifier. And so you have sort of a user's human identity and their mobile identity, and no system knows both of those. In the context of private relay, you have the same decoupling across the multiple relays, that the first relay knows the user's IP, the second relay knows the origin that's being requested, but neither knows both. And then private aggregate statistics, you have an aggregator and a collector, but neither knows both the private identity and the private data. So there's a lot of these, and these are just, this is a very incomplete list of examples of systems that have used this principle. And so really the idea in this talk is to sort of point out the similarity across of these. And so why does this seem to work? Why do people keep using it? Why does it seem to work? And it seems like this is an incomplete reason for why this works. Users often care about hiding their true identity from semi-trusted services and hiding the data or metadata of the requests from untrusted parties. But they don't care about that often, but sometimes they do, whether they reveal that they're a user, some user of a public or popular service. So I don't mind revealing that I'm using such and such service. I just don't want that service to know too much about me. And I don't want others to know too much about me. And users often don't care about whether they can hide a request from the service who is actually providing it. If I'm requesting something from a website and I have to reveal a little bit to get that information, then I'm willing to do that because they are providing me a useful service. There are some cautionary tales and sort of examples of where this doesn't work and why, and then we can use the principle to sort of see what maybe went wrong. It's somewhat obvious in retrospect. So if you take the popular architecture, really not popular anymore, but was a really common architecture, I'd say 15 years ago, which is to improve security of some network or some system X, let's just drop in a security gateway, a middle box somewhere. And that security gateway is going to do all the things we want it to do to improve our privacy, improve our security, whatever it may be. And so in that context, the sender, of course, has all sensitive info, but the gateway also has all sensitive info. That gateway is doing, often was, and still sometimes is doing all processing for that user. And so that means it's seeing decrypted traffic, it's seeing requests that are going out, it's seeing user identity. And so you have to put all your trust in that. And we've always known that. But this is just sort of a way of analyzing it to immediately flag the problem. And then again, the receiver doesn't have all that information. So the value that we get here is that we can quickly identify problems that might arise by doing this quick analysis, this sort of decoupling analysis. This isn't to say that if we show that we've decoupled, we've solved all problems. Obviously, we need to be able to have consider lots of other things. Non-collusion between different parties that are providing a service. Sometimes you get benefits by using hardware enclaves or trusted execution environments. So you can shift trust and therefore shift who knows what. And then of course there are side channels. Even if you decoupled, there are tons of side channels. The side channels are going to be context and protocol specific. They'll still be a problem and will still change the nature of this analysis. So I'm almost out of time, so I'll stop there. Thanks for inviting me.
All right, thanks, Barath. Time for a couple quick questions, if there are any.
Should I read from chat, or what should I do here?
There was some chatter in the chat. Some of it was carryover from the last presentation, though.
Yeah, let's see here.
Okay. Hearing no questions, thank you, Barath.
Thanks.
And we'll move on to the next presenter, which is Mike. So Mike, if you request to share your slides, there's like a little button near the top left that looks like a piece of paper.
Okay.
And then you should be able to drive. All right.
Perfect.
Take it
Can you
away.
hear me okay?
Yes, we can hear you fine.
Okay. So my name is Mike Roselek. I'm a faculty member at Oregon State University. I also happen to be on sabbatical at Cloudflare Research these days. And I'm going to be talking about this paper that's going to appear next month at Usenix. And I just want to thank the chairs for the opportunity to present here. Let's see if I can figure out how to drive the slides. So this is a talk about SSH authentication and specifically authentication using public keys. So I want to review how things currently work in SSH. So when I connect to an SSH server, my client offers a public key and says, hey, do you want me to authenticate under this public key? And the server might say no, in which case my client will offer another public key. And ideally, eventually, the server finds a public key that it likes and it says yes. And in that case, I authenticate by doing a standard kind of signature of some random nonce. That's how public key authentication works in SSH. And I'm here because I want to point out some privacy and security issues with this approach. I think one of the most well-known problems with this is that the server can fingerprint the client. And what I mean is that the server can just say no to all of the client's advertisements. And actually, by default, the SSH client will send all of the public keys that it knows about that are currently loaded into the SSH agent. So the server can see your public keys, even your keys that are, presumably not generated for this particular server. So I want to point out a cool application of this, or maybe it's creepy. I don't know if it's cool, but maybe creepy. And this is what first got me aware of this problem. So back in 2015, Ben Cox had this blog post pointing out that on GitHub, everyone's public keys are truly public. Like you can just look up anybody's public keys. In some cases, that's a nice feature, but he points out that if somebody cared enough, they could collect a massive database of everyone's SSH keys. And so that's exactly what he did. And he did some analytics on these SSH keys. And then a few months later, Filippo Valsorda had this cryptic blog post where he says he invites the readers to SSH to this server. The server is still up. I encourage you to SSH to this server. When I SSH to the server, this is the message that I get. And in particular, I didn't type anything in. I just typed SSH to this domain name, and it knew my full name, and it knew my username on GitHub. So that's kind of creepy. And the reason this works is that my GitHub my public key for GitHub SSH is loaded into my SSH agent all the time because I'm always using GitHub. And so my SSH client offers it to to Filippo's SSH server, and he has a database of public keys. He knows that this public key belongs to this user on GitHub. So this problem can be resolved. You can configure your client to only send keys to the servers that you expect. So this can be resolved with some configuration changes. And so if this was the only problem with SSH, then I wouldn't really have much to say. So I'm going to mention a few other issues with this SSH authentication. Another one is that the client can probe the server. So the SSH client can offer a public key that belongs to somebody else. Let's suppose somebody else knows my public key, then they can offer that key to the SSH server. And if the server says yes, they can conclude that I have an account on that server. Now, the SSH protocol does support a preemptive signature. So the client can provide a signature along with the public key in the offering, in the hopes that this might save a round. But as far as I know, there's no SSH server that has a configuration option that enforces these preemptive signatures to be given. So that's a bit of a problem. Another issue is that the server obviously sees which of the keys was used. So if several keys are authorized to perform an operation on the SSH server, then the server observes which of the keys was actually used. This is kind of fundamental to the protocol. And it's even a little bit worse because the SSH server can prove to anybody that, somebody authenticated under this specific key. So authentication is not deniable. And last, this is a little bit esoteric. I probably won't have time to get into it too much, but the server can say no to all the advertisements, but it can also just say yes to all the advertisements, and it can let everybody in. And it can let people in that it could not have predicted in advance. And that's pretty fundamental to the protocol. All four of these are things that we can sort of improve with our new protocol. So I'll give you the big picture of this new authentication method that we have designed for SSH. It kind of works like this. The client has several secret keys that it knows, and the server has several public keys that are authorized. Those are the inputs to the protocol. And you can see in this case, SK1 is supposed to go with PK1, and SK4 is supposed to go with PK4, for example. These keys can be a mixture of RSA, ECDSA, and so on. So for example, the first public key could be RSA, the second public key could be DSA, for example. All of these can be used together in one attempt. What does the server learn from the interaction? The server learns that the number of keys the client has, and the server learns that at least one of the client's keys is authorized. So it doesn't, in particular, it doesn't learn, in this case, we can see that key number 1 and key number 4 are authorized, but the server doesn't learn that information. It just knows that at least one of the authorized keys was being used, but it doesn't learn which one. And the client learns the number of keys that the server has, and it learns which of its keys were authorized. So it learns that PK1 and PK4 were authorized keys. But in particular, the client cannot learn whether public key PK2 is authorized by the server, because the client doesn't know the corresponding secret key. So the client can't offer somebody else's public key and learn whether the server recognizes it. It can only learn that the server recognizes a key by also holding the corresponding secret key. So this just works without any site-specific configuration. So it's safe for everybody to just put all the keys they know about into this protocol, and you get pretty good privacy guarantees. And then regarding this kind of strange attack that I mentioned on the previous slide, the server can't convince the client that a connection was successful unless the server knows in advance the public key that's going to be used, and it explicitly includes that key in the protocol. So the server can't just say yes to everybody. So this offers a little bit of a protection against some sort of attacks. Let's see. So hopefully I have time to give a bit of a very high-level technical overview of how the protocol works. It just has two main components. So the first component is what we call an anonymous multi-chem. So basically you can think that the server generates a ciphertext and it's addressed to a set of public keys. And the ciphertext is C. And while generating that ciphertext, the server knows that, okay, somebody who has secret key J will decrypt this message to message MJ. So the server learns all these MJ messages. And we need the property that the ciphertext C hides the identity of these public key recipients. So that means that anybody can decrypt this ciphertext, and they might get a dummy value, but if they happen to have one of these recognized secret keys, they'll get one of the plain text that the server has predicted here. So the server sends that ciphertext over to the client. The client can decrypt with all of its secret keys. And so now some of these decryptions are equal to the values that the server already knows. And so to tell whether they have any in common, they use a private set intersection protocol. So in private set intersection, each party has a set of items. And we use a variant where the client learns the intersection of the items, and the server only learns whether the intersection was empty. So in this case, if the server learns that the intersection was non-empty, it means that the client must have been able to decrypt under one of these good secret keys. And that's all the server needs to know in order to decide on whether to authorize this connection. So from our technical contributions of the paper, maybe that's less interesting to this audience, but we show how to generate this multi-chem that simultaneously supports the different key flavors that are supported by SSH. And we do this new modification of private set intersection. This way of proving that the intersection was non-empty is kind of a new thing, and we show how to add that to the state-of-the-art PSI protocol. And in the paper, we have a full UC security proof. So this is a composable security, kind of the best kind of security that we know how to prove for an interactive protocol like this. Okay, so finally, I want to just mention the performance of this protocol. We implemented this as an extension of OpenSSH, and it's quite practical. So I mentioned that the protocol supports RSA keys and elliptic curve keys simultaneously, but the RSA keys are much more expensive. So for the worst case, let's look at if all the keys are only RSA keys. That'll be the worst case in terms of performance. And the best case in terms of performance is if all of the keys are just these elliptic curve keys. And we didn't find any difference between ECDSA and EDDSA. There's very little difference there. So I just lumped them into one category as elliptic curve keys. So in a realistic setting where the client has 5 keys and the server has 10 keys, I think that's a realistic setting for a kind of a small GitHub repository, let's say. Even with RSA keys, 60 milliseconds, and with elliptic curve keys, it's like instantaneous 9 milliseconds. I mean, 9 milliseconds is not instantaneous, but for authenticating a connection, that's pretty good. A more extreme example would be the server has 100 keys and the client has 20 keys. That's like, you know, a GitHub power user connecting to a really popular GitHub repository with 100 maintainers. Even that is still, I believe, within the realm of reasonableness for authenticating a connection, even with RSA keys. We try to take this to the extreme and imagine a server with 1,000 keys. So that's a server that authorizes 1,000 different public keys to be able to connect. So with RSA keys, that's a little slow. It's over a second, but even with elliptic curve keys, less than a quarter of a second. So again, I think it's pretty reasonable. So that's all I have. This is my last slide. It's just a summary of what we provide in this new protocol. The protocol basically gives the minimal amount of information to the server. The server learns only one bit of information, that it learns that the client has some authorized key. So if you want more information, I have a link at the bottom. The paper is on ePrint, and I'll be happy to take time for questions.
Right,
I
thank
see
you.
a question in the chat from Chris P. Concrete performance. This was like total round trip time. So from the client's perspective, from the time you say, I want to connect to the server, it includes the TCP setup as well, I think. But these were two servers on the same LAN. So the time from saying connect to the time that we can send the first application command to the SSH server.
Might not be on.
Yeah, if there's a question, I can't hear it.
When in doubt, turn the microphone on. This is Daniel Kahn-Gilmore from the ACLU. Thanks for this presentation. Thanks for working on this. This has been a long-standing feature of the SSH protocol, or bug, depending on your perspective.
Yes.
Have you thought about how you would apply this to common patterns right now, like the Git-based forges, GitHub, GitLab, etc., that have everyone using one account? Everyone, you know, if you configure SSH to GitHub, it's git at GitHub.
Yes.
And then your SSH key is what does the split. So they need to know what it is to make that work. Have you thought about how to apply this there? Or do they have to change their pattern?
Yeah, that's a great observation. We do have a section in the paper where we talk about GitHub as the most obvious application of SSH. So it's true that at the time that you run the protocol, let's see if I can illustrate with a picture, it's easier for me. At the time you run the authentication protocol, the server has to know which keys are authorized. And if the server only knows that some GitHub user is connecting to some repository, that's not quite enough information. So it turns out in the SSH flow, the client says, I want to authenticate to this user. So in GitHub, it's I want to authenticate as git at github.com. And then the authentication begins. So there is a place in the SSH flow where you can say, maybe it's, I want to authenticate as repository name at github.com. the server sees repository name and goes to see which of the keys are authorized. So it would work if you could make that change to the GitHub flow. And of course, if you wanted to support this as an optional thing, you could. It would be like repository name at new.github.com or something. So by connecting to new.github.com, you would signal that you want to use this new authentication protocol, and then the username would be the repository name, and that's how we envision it's working. But yeah, it would require some changes for sure.
All right, and there's one more quick question in chat. If it's a,
Would you like me to take
more
this
it's a quick
online?
answer. If it's a quick answer, we can answer it now. If not, then we can take it offline.
Different configuration and constraints server side. I don't think I completely understand what this person means by configuration constraints. Maybe we'll take that offline and I'll ask for a clarification.
Okay, sounds great. Thank you, Mike.
Thanks.
All right, I guess the last presentation is from Mallory.
All right, this will be really quick. This is a draft that has been adopted by the working group. And so I'm here to give you a really short presentation about why I think we should keep working on it, but I'd like some help. So next slide. This is just a draft of what this is just a summary of the table of contents for what this draft does. So in trying to define what is safe internet measurement, I think the focus on consent is good. I did a bit of a rework on the table of contents. So rather than putting case studies for each of these versions of consent, they're now just kind of subsumed into their subsections on informed consent, proxy consent, and implied consent. And then there's a long, but maybe not exhaustive list of safety considerations because it is about safe internet measurement. And I'm pretty happy with that list as it is right now. But always there could be things that are missing from it. And then there's a final section on risk analysis. So next slide, please. There are quite a few open issues, mostly because the original author, Ian Learmonth, who has done the vast majority of the work, already put those issues in there. They have not all been solved, but mostly they're quite low-hanging fruit in terms of he's identified some really good citations that are within scope of the document. They just need to be elaborated within the structure. And here's a sort of short list of those 6 open issues. You can see right there, they're pretty obvious. Next slide, please. Then I think so, yeah, there's a really basic update to this, which I think makes the structure a little bit more straightforward. I'm going to also plan to send a message to the PEARG list for those that aren't here or participating online in this meeting to get more feedback on folks who might be interested in suggesting text for the open issues or reviewing the current version to make sure. I think I have 2 questions about review at this stage. One, is the table of contents complete so far? And then 2, if there are definitely missing sections that we already know about. But the last thing I'll say before maybe people have comments or want to volunteer to help is just that you might have seen the IAB announce a workshop coming up, like Q4, I guess. It's slated for late October, and submissions for papers are due, I think, at the end of August or early September, but it's on measurement techniques in encrypted networks, which I think is a place where we could present this draft in whatever version it's in and get a bit more feedback from folks who are also thinking about these issues. The workshop, I think, turns the concept on its head a little bit, because what it's trying to do is make network measurement a little bit easier, or try to solve some of the sticky issues with network management in encrypted environments. And this draft is sort of coming at it from like from a safety and privacy perspective, you want to make that measurement safe, if that makes sense. Anyone have any questions? Or so my plan is to continue to work on this, submit a paper to this workshop, and then get feedback from there, as well as on the list from all of you folks. Comments or questions?
Doesn't look like there's any questions, but one recommendation, now that the IETF is working on privacy preserving measurement, that's certainly a group that will probably need some guidance in terms of how to use the systems they're developing, DAP specifically. So I wonder to what extent, either this document would benefit from the work that that group's doing, or that group would benefit from the work that's being developed here. But it seems like there's some cross-pollination that should be happening as we move forward.
I think you're making a really good point. And if there's anybody who actually has a viewpoint on how this draft should fit in with that work, especially those who are involved in PPM, I'd really love to know that now, or we can talk in the hallway or at some point in the future. But because I think the idea is that this would maybe be, this draft, because it's in the IRTF especially, would kind of be making a broader sort of approach to the issue, and then PPM would maybe then, yeah, as you say, sort of take advice from it. Okay, thanks. Yeah, no, go ahead.
I think we're good to wrap up. Just one, I guess, note that draft censorship just cleared last call, so we will finally have an RFC soon, maybe, hopefully, after 7 years. But yeah, thanks all for coming, and see you next time.
We'll know very quickly if it works or not.
No, it works.